that this deterministic rule is as random or as regular, whatever you call it, as a coin toss. So it's in that sense that deterministic dynamics can be extremely random.
And the string size must go to infinity.
Pardon me?
The string size must go to infinity.
Go to, yeah, string size. Or even if you give me a finite string, that's even better, right? I can give you many initial conditions which will generate that finite string.
Actually, you can if it's a finite string, there are finite set of possibilities, and you can always match one to one.
Yeah, exactly. So it's true in the infinite case. Then it's not trivial. So, not that the deterministic rule is random. There's no stochastic put in, but the outcome of that deterministic rule cannot be distinguishable from that of a purely random variable, like a coin toss. And that's true for all these chaotic, all these hyperbolic systems. That's always true. So it is in that precise sense we're talking about. Now let's push this a little further. In this particular case, since this L and R is directly one-to-one correlated with the A's, if it's L, I know the A is 0. If it's R, I know that the corresponding A was 1. It also means that given this string sequence, I can reconstruct X1 completely. Even without worrying about where the hell it went, actually, I can reconstruct this whole thing. Any partition of phase space which reconstructs the dynamics faithfully is called a generating partition. And this is a generating partition. Pardon me? Yeah, any partition, if the symbolic dynamics reconstructs the actual dynamics, this implies what's called a generating partition. And in this simple model system, we are very lucky to have a generating partition. More complicated systems, very hard to find a generating partition. What people do instead is something slightly different. After all, this thing is mimicking some kind of random process in this sense. So we expect that once you have coarse graining in the dynamical system, it starts looking like a random process. Then there are partitions of the phase space in specific manners, such that this symbolic sequence could be a Markov chain. It could look and have exactly the same properties as a Markov chain. In that case, you have what's called a Markov partition. Then the whole machinery of Markov processes, which is known in great depth, can be used to analyze the dynamics once again. In particular, if you have maps, one-dimensional maps for instance, which are piecewise linear, etc., you look at all the fixed points in the map, you look at all the points where the map changes slope or has discontinuity, etc. Use those as the boundaries of your cells and the pre-images as boundaries of cells. You're guaranteed to have a Markov partition. This one here was both a Markov partition as well as generating partitions. In fact, what's called a Bernoulli partition. So it's a lot of special things that happen here. The same thing will be true if I further refine it. If I say I break at 1/4, 1/4, and have 4 cells, you can still get the dynamics regenerated. If you break it to 1/8, 1/8, etc., you still get it, etc. So there are many techniques which borrow from symbolic dynamics, which borrow from number theory, which borrow from theory of Markov chains, which you can bring to bear on this problem.
So can you briefly explain what is Markov process?
Okay. I assume that everyone knows what a Markov process is, but very quickly, it's the following. Going to this. If you have a random variable, which is a function of time, for instance, then it is specified by specifying the, let's look at the variable which is continuous, for example, or discrete value, doesn't matter. So let P of x comma t be the probability that the variable takes the value at the time x. Let's talk about discrete valued variables, so I don't talk about densities, talk about this guy itself, probabilities themselves. Then I can ask what's the probability that the variable takes the value x2 at time t2 and x1 at time t. Then I ask what's the probability that it takes x3 at time t3, x2 at t2, etc. And this random variable is described by an infinite set of joint probabilities. Every random variable is described by an infinite set of joint probabilities. However, this fellow here, by definition, is equal to the probability that you have x2 at time t2, given that you had x1 at time t1, multiplied by the probability that you have time at t1, you have x1. By definition of this conditional probability. Similarly, P of x3 at t3, x2 at t2, x1 at time t1 is, now each of these is a different function, so let's distinguish that. P1 is a single argument time argument, P2 is a two-time argument guy, this is two-time argument, this is one-time argument, this is three-time argument guy. This is equal to the conditional probability that you have P3, x3 at time t3, x2 at t2, and x1 at t1, multiplied by the probability that you had x2 at t2 and x1 at time t. This particular thing, this is P2, can be written in this factored form. This fellow, however, has two preconditions, both this and this. The next one will have three preconditions, etc. Now, a Markov process is one where the immediate past is all that matters. Previous history is forgotten. It's the equivalent of first order differential equations, where only the present state controls the future and the past is forgotten. The history of how you got to that state is forgotten. So Markov processes are the analogues of society, means there are no community certificates. You are what you are, no birth certificate is necessary. Nothing to do with where you came from at all. Only the present guides the future, not the history at all. So this dependence, if it goes away in all the rest of the probability densities, then it's called a Markov process. Which implies immediately that the n-time probability can be written as a product of two-time joint conditional probabilities multiplied at the end by a single one-time probability. So all the physics is contained in this two-time density. Given this, what's the probability of this? And you can go even further. You could say, if this thing is a stationary random process, namely there's no dependence on the absolute origin of time, but only on time differences, then this becomes a function, P2 of x2, multiplied by T2 minus T1, given that you had x1 at time t. Okay. So it becomes a function of one time argument, some function, which will depend on these guys as well. Moreover, if you assume that the system has enough mixing, that is ergodic, then it also implies that the limit of this fellow as T2, it also implies, by the way, that this quantity here, P1 of x comma t, should become independent of time. Because time origin doesn't matter at all. You remove it and it becomes independent. Moreover, you also expect another thing. You also expect that the limit, as t tends to infinity, and this quantity, let me call it t, should not depend on x1. Because that happened at time, some arbitrary time t1, and this is the interval after time t1. And as that interval becomes very large, it shouldn't depend on this. It should tend to a limit. And that limit must be time independent. And if there is stability in the problem, you're not going to a new equilibrium or something, this will of course become equal to P1 of x itself, of x2. Independent of the initial condition x2. So in other words, for a stationary Markov process, the single conditional density involving two arguments fixes everything. And you write equations for it. You think a little bit about it, you discover that every equation you write in physics is always for a conditional probability. I can't write the equations for absolute probabilities. It makes no sense. Always for a conditional probability in every area. And there are equations for this. If it's a Markov process, this satisfies what's called a chain rule or a Kolmogorov equation. Happens to be an integral equation, which is nonlinear. And then you make further assumptions about transition probabilities and so on. It's converted to what's called an integral differential equation, which involves a transition probability. And if you make even further assumptions, you can convert it to what's called infinite order Kramers-Moyal equation. More assumptions will make it into the Fokker-Planck equation. And you can then map it onto a stochastic differential. So there are many, many techniques for doing this. The gas in this room, if it satisfies the Maxwell-Boltzmann distribution, you can ask the question, oh, suppose I start with a particle whose velocity is not, it's random, some random velocity. What's the probability density that the velocity is v at time t, given that it was v naught at time t equal to 0? Then the answer is that at v equal to v naught, at t equal to 0, there's a delta function at v naught. As t tends to infinity, I expect this fellow to equilibrate, so it will become the Maxwellian distribution for any component of the velocity. And then the problem is, how does that at t equal to 0 become this at t equal to Maxwell? And the answer is, this problem is modeled by Gaussian stationary Markov process, and there's only one such process. It's called the Ornstein-Uhlenbeck process. And basically what it says is this delta function broadens out and broadens out more and drifts till the mean becomes 0 and it hits the Maxwellian distribution. And that satisfies the so-called Fokker-Planck equation. That's a Markov process. The moment you relax the Markov assumption, you're out of it. You do a more complicated thing. But just as in the case of mechanics, you say, oh, the particle obeys second order differential equations, it's too hard for me. But you go to phase space, it obeys two couple first order equations. In the same way, if you expand the state vector and choose the right number of variables, then I think everything is a Markov process. But a multidimensional Markov process. In exactly the same way. So basically that's what the Markov process is. And in discrete time, it becomes a Markov chain. But a Markov chain, all the properties are known. Huge amount of properties. By just a historical note, Markov did his work in 1906, published it in 1906, 1 year after Einstein wrote the Brownian motion paper, which essentially was all about the Wiener process, a kind of Markov process, sort of fundamental Markov process, written entirely on physical grounds. But even Markov was not the first guy. Louis Bachelier in 1900 wrote a thesis on finance, which had essentially the Brownian process completely, did the mathematics of it without using that technical term. And then it was lost for a lot of years till Levy rediscovered it in the 30s and so on. So things sort of. It's interesting that the main use of Wiener processes today is back in finance, once again. So 100 years later, we've come full circle back to money. So what I want to do in the few minutes available is to show you what I promised earlier, namely, what does one do if you coarse grain phase space, and what information can you get from the invariant measure if you have restricted information on it. So here's my phase space, and I'm going to coarse grain it in this fashion into cells, and let's call the cell C sub j. And I now assume there's an invariant density. The integral of this invariant, I don't need to assume an invariant density, I need to assume an invariant measure. So this mu j is the measure of the cell Cj. That's just, if you like, the integral of d of x, rho of x over Cj. You don't need this formula, but basically you need a measure. That will give you, if the total phase space volume is taken to be 1, then this mu j gives you a given orbit, a typical orbit. You wait for an infinite amount of time, keep track of all the total time that it spends in the cell Cj, then that fraction of the total time is mu j. So that's a very straightforward interpretation. Pardon me? Well, this fellow is wandering all around, but every time he comes to Cj,
Elementary volume element.
Pardon me?
Elementary volume element in the phase space.
That's a volume element in phase space. Now, if you got a trajectory that's going all around, or etc., and I keep a track of the total time that it spends, total fraction of the time that it spends in this cell, that's the measure. It's a simple way of understanding. provided this trajectory is ergodic, etc., and visits it. And because it is not a uniform density, you spend more time in some regions, less time in certain regions. Just like our pendulum spent more time here, more time there, less time. Now, I define the following quantity. I define a generalized dimension dq, parameterized by real number q, as follows. It's a generalization of the idea of a fractal dimension as well as the idea of Shannon's information and the standard thermodynamic definition of entropy. So it's equal to 1 over 1 minus q limit, and let's put the limit to the side. Limit epsilon goes to 0, 1 over 1 minus q log of a summation over these cells, j equal to 1 to n, and of course the cells will depend on how small the cells are, and let's say that I have a linear dimension epsilon which tells me the size of the cells, and anyway I'm going to take a limit in which the cell size goes to 0 in a formal sense. So n of epsilon. The measure of the jth cell raised to the power q, measures are all non-negative, divided by log 1 over epsilon. That's my definition of this number dq.
What is Q?
Pardon?
What is Q?
Q is any real number. So it's parameterized by this real number q. I define a family of indices dq by this process. Q runs from minus infinity to infinity. For each q I calculate this. Then look at what happens if q is equal to 0, for instance. d0 is equal to, I put q equal to 0 here, its limit epsilon goes to 0, a summation, this is 0. So it's just 1 here and it's just the number of cells, if you like. So limit log n of epsilon over log 1 over epsilon. Now all of you know that this is the fractal dimension. For a regular object, it will just give you the Euclidean dimension. Otherwise, it gives you the fractal dimension. If it's a fractal object, it will give you the fractal dimension. Pardon me? I mean the box counting dimension. I don't mean the Hausdorff dimension. So I'm not going to distinguish here in the remaining time between the Hausdorff dimension and the box counting or capacity dimension, but it's just the box counting dimension. And the number of boxes.
So why is this fractal then?
Pardon me?
No, why is this not fractal?
Are people familiar with fractals?
Yeah, that's right. Why is this not?
So what you do is, if it's a completely self-similar deterministic fractal, what you do is you take a unit, you break it up into a certain number of units, you find out the scale factor, epsilon, and divide the number of new pieces divided by 1 over the scale factor. So that's what it is. So if you took this 0 to 1, the famous snowflake curve, for example, this fellow is broken into 1/3, 1/3, 1/3, 1/3. So this is 0, 1, and this is 1/3. You've broken the original line into 4 lines, so n is 4, and each of them is 1/3 the earlier thing, so 1 over epsilon is 3. So the fractal curve of dimension of this curve is log 4 over log 3. So it's in that sense. Or if you took this Cantor set, somebody asked me about the Cantor set. Yeah. Let me quickly mention what the Cantor set is so that it plays a role here. In fact, let me go back and, I don't know when I do this, but let me go back and look at it in the context of a map. Someone asked what happens if this logistic map goes outside the unit interval, 4 goes greater than 1. So instead of doing the logistic map, let me do the let me do the tent map, but now I'm going to take slope not 2 but 3. Then this curve from 0 to 1 goes out like this and comes back, and this guy is 1/3. And this fellow is 2/3. That's my map. And I ask what happens to this guy. Well, let me for a moment extend this map all the way, minus infinity to infinity, and you'll see what goes on. That's the bisector. I start at a point between 1/3 and 2/3. I go here, go to the map, the bisector, come back to this fellow, come back to this map here, to the 45-degree line here, come back, and I'm gone. That particle, that initial condition escapes to minus infinity. So any initial condition between 1/3 and 2/3 on iteration will disappear in one shot. Then there are points here which after one iteration fall into this interval, and after 2 iterations they will disappear out of this box. So the question is, what's left? What's left is the set of points where you take the unit interval 0 to 1, eliminate all points between between 1/3 and 2/3. The open interval between 1/3 and 2/3. So you're left with 0 to 1/3, 2/3 after one time step. After 2 time steps, you're left with points. Points from here would escape, the middle third would escape. So this 0 to 1/9, that's 2/9, that's 1/3, and this piece will become 4 pieces of smaller, of length 1/9 the original length, etc. And you keep doing this all the way to infinity. Now the fractal dimension is easy to compute because each piece is broken up into 2 pieces at each step. So that's log 2, and each piece is 1/3 the previous piece, so log 3. This is d0. Fractal dimension is between 0 and 1. So it's a dust. It's not a line. It's a dust. But its fractal dimension is just a set of points, but the fractal dimension is between 0 and 1. However, this set of points is not countable. It's a dust, but it's not countable. And the reason is, you could write this number between 0 and 1, you could write any number, not just in binary, but in ternary. You could use the symbol 0, 1, and 2, and write any number as a string. So 0.120021, blah, blah, blah. Now if this initial digit is 0, then the original number is between 0 and 1/3. If it's 1, it's between 1/3 and 2/3. If it's 2, it's between 2/3 and 1. And now what you're doing is removing the middle third each time. Therefore, in your surviving set of points, they will have ternary expansions in which the digit 1 will never appear. But 0 and 2 appear. However, that's 2 digits. Now you can regard the 0 and 2 like binary numbers, and they are uncountable. So what's left is still an infinity of points which is uncountable. But the dimensionality, the fractal dimensionality of that set is no longer 1, but it's actually log 2 over log 3. But the length of what's left is 0, absolutely 0, because you're killing what's left. At each time the original length becomes 2/3 the original length. After n steps it becomes 2/3 to the power n. And as n tends to infinity it is 0. So the Lebesgue measure of this dust, Cantor dust, Cantor said, the Lebesgue dimension is 0, no length at all. The set of points is uncountable, and the fractal dimension is log 2 over log 3. Like length, dx. So making a precise definition of it, the usual dimensionality is 0. Certainly the topological dimension is 0. And you can see that you can also calculate the length that is left, and each time you discover that it tends to 0. Okay. Now the length of what's thrown away is 1. The total length of what's thrown away is 1. Because first time 1/3 is thrown away, then twice 1/3 squared is thrown away, then 2 cubed, 1/3 cubed is thrown away, etc. And you sum the geometric series, you get the fact that everything that's thrown away is length 1. So that's a simple example of a fractal. On the other hand, this is giving you a lot more information. Look at what it does at q goes to 1. As q goes to 1, oh, by the way, one physical fact you can immediately see from this is that because it's a sum over a probability measure raised to a power q, it's clear from this that if q is a positive number, large positive number, then those cells in phase space which are visited very often, whose measure is large, will dominate. So positive Q, large positive Q, dq will tell you something about those cells which are visited most often. But the advantage of this definition is that if Q is negative, then those cells that are rarely visited get dominance, because this fellow here, mu is very small in that case, raised to a negative power, large negative power. So that dominates. So the advantage of this dq is that it probes, over all Q, it probes everything in phase space. Those cells which are rarely visited as well as those which are visited very, very frequently. And if Q is equal to 1, then what happens to this? This becomes singular because this fellow here blows up. But then if Q is 1, this is log 1. And log 1, of course, is immediately equal to 0. So you get 0 over 0 and you need to take the limit. So let's do that. This mu j to the q, I'll write as e to the q log mu j. And this number I will write as, this thing here, I'll write as e to the log mu j. Taylor series about q equal to 1. That's mu j itself, plus q minus 1, derivative of this guy with respect to q. That gives you a log mu j. So you have a mu j log mu j, plus order q minus 1 whole squared, etc. And now I got to put the summation and then do a log. So I put the summation here and I get a 1. So this becomes log of 1 plus summation, and a q minus 1 comes out. Summation j equal to 1 to n of epsilon, mu j log mu j, plus higher orders in q minus 1. In log 1 plus a small number, to leading order, it's a small number itself, q minus 1 itself. So I get rid of this log, I have this guy here, and this q minus 1 cancels with that, gives me a minus sign, and therefore this becomes equal to, apart from this epsilon limit, etc., it essentially becomes summation mu j log mu j with a minus. And of course, that's the entropy, or the information. This minus sign is the information. Pi log 1 over Ti. Pi is the probability. So D1 is called the information dimension. Exercise, show that D2 is the correlation dimension. So D2 will measure the correlation between different parts of phase space, etc., etc. So there's the whole infinite sequence of these guys, and the interesting thing to ask is, what does it look like? What function of, what does it look like? So, can I have 5 more minutes? Then, let's look at a case, again our favorite one-dimensional map, and see what this dq does. So I'll take the unit interval, let's see how fast I can do this, and I'll partition it into equal cells. So I'll break it up into n cells, each of size epsilon, so that is equal to 1. This is 0, this fellow is 1 over n, this fellow is 2 over n, etc. And this is cell j, Cj, and it runs from j minus 1 over n to j over n. That's my cell Cj. And then I'm going to take the limit in which n goes to infinity or epsilon goes to 0. So mu j equal to an integral from j minus 1 over n to j over n dx rho x. And I'm going to take n becoming very large. So what does this measure become? This goes to the size of this interval, which is 1 over n, times rho of the midpoint of the interval, j minus half over n. If n is large enough, this is the meaning of integration. Right? Now, let's calculate what this dq does. So dq equal to limit n going to infinity, because epsilon is 1 over n, 1 over 1 minus q, log summation from j equal to n, 1 to n, of this measure raised to the power q. So 1 over n rho of j minus half over n raised to the power q over log n. That's the exact formula, and we need to evaluate this guy here. If the measure was uniform, if rho of x was 1, then the answer is very trivial. Because if rho of anything is 1, this fellow goes away. It's just a constant. You get n to the minus q, and this is log n to the power 1 minus q. There's n of these fellows. So you get n to the 1 minus q on top, n to the 1 minus q below, log of each.